All right, I think I'm going to talk about science a little bit. Not really science, things that people who are scientists claim to be true. We're going to be logical about it. It is entirely possible, and I'm not the only person that thinks this, it's entirely possible that one day we will build a telescope so powerful that we will stare straight off in one direction into the universe. And we will zoom so far. And we will go so far beyond the farthest that we've ever seen. And then what we'll see in that telescope is the back of our own head. And then us turning around to look. It's entirely possible that that may be the case. And highly likely that there is a rational, scientifically demonstrable explanation for such an effect. Curvature of space or something. So I got curious about what's the farthest object that James Webb has managed to see. And they want to talk all about the magnification and everything else. And now we've got what it appears to be as a distance. So we live at the center of a particle horizon that is not a physical thing, but is a side effect of the vastness. Within this horizon, this limit of view, at the outskirts, what this is anything that emits light from within this radius. The photons are able to travel across the universe and be observed by us. And the vastness of it causes this light to redshift over time as it loses energy and slows down. And eventually, only the dimmest, weakest light, and when I say light, I'm talking photons, radio waves, infrared too. That's all kinds of light. So photons is what I'm really talking about. The particle horizon is the theoretical furthest that anything can emit light or any kind of photon that could reach us before it loses energy and simply evanesces into the vacuum energy field. Because energy is neither created nor destroyed, it is only conserved and transformed. Beyond the particle horizon is more. Particle horizon is, for visible light, approximately 13.9 billion light years from here. And it only exists like that to us from this place because this is where we're at observing. It is 13.9 billion light years from here because this is where we're observing from. But an observer over here will observe a 13.9 billion light year radius from there. It's not a real horizon except to us. It could be thought of like in a video game where fog or murk or darkness masks off the level from a top view or whatever, and only so much shows. That's the particle horizon. There's still stuff beyond it. We can't see it from where we're at. It's too far. Now, infrared travels even farther than visible light because it's dimmer. It's a little bit lower energy, but it still does. And radio waves, there's a radio horizon. There's a microwave horizon called the cosmic microwave background. And it is supposedly kind of the echo of the Big Bang just after the fact, as far as some kind of bright flash that eventually, over the distance of the light traveling from that to us, appears as microwaves it's all just the illusion of the end of the furthest distance, but it's really just the furthest distance we can discern. And it's an important thing to note because we don't know how big or precisely what the curvature is of the universe. We suspect it's curved. When scientists are like, oh, the curvature of space, and they've measured it on a smaller scale with stars and black holes and sometimes galaxies. But as far as discerning what the curvature of the actual cosmos itself is, first we have to know how big it is. We have to know what it's doing, and it seems to be expanding, except at every direction you look, it's expanding in every direction. This seems to be impossible. And I don't know about you, but I don't really feel like I am constantly just expanding. I mean, maybe we are. Maybe I'm personally bigger now than the Milky Way galaxy was just after the Big Bang when it first formed, like in literal, what it stretched from. But the distances and the speed of light are the same. So James Webb Telescope can see farther than any other telescope we have can see with zoom and detail. Radio, you can't really do it like that. It doesn't work that way. The wavelengths are too big. If you wanted a focusable, lensable, zoomable, you have to do like the Event Horizon Telescope, but way bigger if you want to get any kind of actual resolution. So mostly what they're really getting is photosensors are getting zeros and ones as far as touched by photon, not touched by photon in specific wavelength. And then they filter down for the near in. It's like focusing, and there's probably a lens, but it gets to where they can take a little area, the teeniest little area, and zoom in super hard on that. And they can do some deep fields too. They can, it's like the Hubble did the same thing. It's just galaxies and galaxies and galaxies, like stars in the sky. But each one of those little dots is a galaxy. And some of them are galaxy clusters. It's huge. But the thing is, because we suspect space to be curved, and we're not 100% sure on how it all works, we have to accept the possibility that the curvature is such that we might be like in a photon ring situation around a singularity, where all the light that we are seeing is traveling in a gargantuan circle, and that at some point or another, we're going to be, so the thing is, we wouldn't literally see ourselves. We might find our sun with Earth. If we're able to zoom in enough to discern that kind of detail, we could find our planet, but who knows how many billions of years ago that light would be from. Wouldn't it be wacky, though, if it contained us, too? But, so, the problem is that you've got this apparent distance. You've got wavelength measurements, polarities and such, the different quanta of a photon, quanta being, or like quantum information. These are beyond just is light, is not light. You've got information that contains wavelengths, frequencies, amplitudes, and so you can calculate, if you know what this was emitted by, roughly what the actual like visible light frequency it would be emitted from is, and how it has gone for so long before finally reaching us, that it's sunk out of the visible light range. And they look at it and they calculate it and they figure it. And they say, okay, so thinking that this is a star, it's probably got this spectrum of light. And from this possible spectrum of light, of visible light, being emitted back there to infrared means X number of light years of distance. How many years that photon traveled before being, photons, there's obviously more than one. But any given photon at that distance, making it to us is pretty tremendous. So being able to look and zoom and see and resolve it and measure it and figure 28 billion light years. God, what is that? 600,000 kilometers. Is that right? I don't know exactly what the measurement is, but that's like, let's see if 10K is 6 miles. So is that 296,000 miles? Isn't that right? Something like that per second is the speed of light. So that distance per year of travel for 28 billion years. And then, okay, so when do they think the Big Bang happened? When did the universe come into being as we know it? Well, you got this moment of singularity and a quantum fluctuation in a foot, and then everything was about the size of a baseball, and then it's expanded up to, hyperinflation faster than the speed of light. It expanded, which the speed of light in a vacuum, for those who are curious, is represented by the letter C because it is actually the speed of causality. In a vacuum, a massless particle may move at the exact same speed as cause and effect, which is to say instantaneously, point to point within close range. Cause and effect. And even afterward, you can see cause and effect happening everywhere. So, space-time ripples may or may not be bound by the speed of causality for like gravity waves. Sorry, gravitational waves. Gravity waves are a cloud thing. So they think that the universe is about 13 billion years old. And if us and the farthest point we can discern are in the same place at the Big Bang and move outward for 13 billion years, it would be 26 billion light years between us. But then there's also all of the universe on the other side of us from what we're looking at, which is the same size, which means that it all would have come from a central point where we're located to that particle horizon in 13 billion years. And there's more. So the universe may be expanding at faster than the speed of light. And our theories say that at moving faster than the speed of light, you would be moving backwards in time. So we're looking at things that are farther than we're supposed to be able to even think that there should be stuff, finding more. And hence the stuff behind that. It's not like we looked at the farthest thing and after that it's a black void. It just keeps going. And that's looking in that direction, which means it goes in that direction too. And if we take a telescope and train it on both directions, might we find the same star? That's just what I want to know. But so we've got these black holes, often congregating around the center of galaxies, possibly causing galaxies. We don't know. There's evidence for rogue, free roaming, supermassive black holes. We know that there are black holes that just free roam of a smaller size, stellar mass. We have theories about super tiny microscopic primordial ones, but I kind of question that given that we don't understand the other things I was just talking about. So how could we come to that conclusion? So we've got black hole mergers, we've got neutron star mergers, we've got supernovae causing collapsars to collapse. We've got places where space-time shakes, jiggles, ripples, is twisted hard, possibly torn, we don't know. And this all just flippy flaps throughout the cosmos constantly. They're pretty sure now from what they're measuring. They're like, it's probably just ringing and singing in space at all times on these gravitational wave levels, which we're talking about miles long, single wave, hundreds of millions of miles long, single wave wavelength. that these ripples are just moving and tsunamiing and going, and some little smaller ones, and the echoes of all these mergers going constantly, to a being moving at the speed of light, able to listen to the entire cosmos while moving at the speed of light. This might sound sped up then. Who knows? Or it could just be. So here we are, living on a little planet, trying to figure out the environment in which we exist. And it appears to be an infinite cosmos of these weird intertwining strands of galaxy supercluster clusters, all of which are being kind of whipped and moved around a point A and a point B that they all appear to be moving to. And the entirety of it appears to be larger than is rationally possible given the amount of time it appears to have been here. So my question is, have we just misunderstood what we're looking at when we examine what we think is the fabric of space-time around us, when we're measuring things like Einstein rings and, using standard candle stars and things like that? Is it possible that our supposition of things like the Hubble constant or the Hubble tension specifically, the different measurements render different attempts to measure render different results of measurements as to what the rate of expansion of the universe is? So depending on how you look at it, it's expanding at a different rate. And it cannot literally be expanding at different rates at the same time, depending on what frequency it is. Unless every photon moving at light speed is on the brink of time travel. It's an awful busy universe. That's an awful lot of stuff going on that can't really be seen, heard, touched, felt. The most extreme experiments we have to come up with. Miles long corridor with a laser, and then there's a miles long other corridor with a laser, and it's long enough that the lasers make it back and forth. They're bright enough to shine it, and they measure the time it takes. And if there's even the slightest anything off from the zero, that's a gravitational wave causing space-time to just slightly, and we can barely sense them. So is it possible that our thoughts about what the quantum information of the photons we receive from great distances that we use to attempt to measure distance with are being distorted by all of the ripply waves and such that are just going around through the cosmos because of all the space-time stuff that's constantly happening, the low grumble of black holes? You can think of it as sound in a sense because it is vibration, but it is so low, 60 octaves lower than the ear can hear. It's hard to explain what that means. So low. Years of wavelength just to get one wave. If it was a tune, man, you'd have to go for eons, millennia, and then maybe you'd have a second's worth. So how do we know that the time of the expansion of the universe, based on measuring these differing depending on which one thing you're measuring, rate of expansion, how do we really know that it's only 13, or that it's, oh my gosh, that's really 13 billion years old? But that we find things that are farther out, that if it was from a mutual center point expanding, unless you're telling me that each individual moment of space-time, each tiny little like Planck length, is also simultaneously constantly expanding, that means that we and literally this end of the cigarette to this end of the cigarette, it would therefore be relative to each other moving away faster than the speed of light. Really? Pretty sure my time-traveling cigarette would be exploding with gamma radiation right now. It's really curious to me that nobody else has really seemed to put this all together. Nobody in the scientific community has bothered to say, wow, that's a whole lot of crazy shit that if it was all happening at the same time, like the evidence suggests, we would be getting constantly ripped apart by, differences, conflicts between various levels of observable reality, which is clearly not happening. So at some point, one way or the other, we're going to end up seeing the back of our own heads looking through a telescope if we look far enough into the cosmos. And at the same time, try and reconcile the fact that we are both moving and not moving at the same time, at rest and faster than the speed of light at the same time, relative to points within us. Because if every Planck quantum level space, the tiniest tiny, is constantly expanding at the speed of light with the Big Bang and everything else, all points relative to all other points within the entirety of all of the universe would be simultaneously exploding faster than the speed of light, which is to say backwards in time. So I think we've miscalculated or misunderstood how to read it. Or that all of that shit in the underneath background of the, call it subspace or whatever, it's the space-time gravitational wave ripples and the weakest photons coming from the farthest possible distance. The other alternative would be that all of that stuff is crazily true because we're like inside a black hole or something. And then that means that we, as stable individuals living lives while simultaneously occupying the inside of a black hole for a universe, would be like the far future they humans from Interstellar. Does that make us gods? I don't know. So that's what I got. I had some questions. I hope this has been enlightening or given you something to think about. I'm not saying science is wrong or bad. What I'm saying is that there's a lot of weird stuff that some of these people seem to either have a hard time reconciling or are not trying to reconcile. And if I try and reconcile them, I pretty quickly come to, well, this seems like this and this seems like this. How could that be? And typically speaking, historically, theories that come about with a how could that be that doesn't have a solid straight answer, something demonstrable with an experiment, gets thrown out. What I'm referring to is the current paradigm of cosmology and astrophysics. I think we really don't understand. We need a breakthrough because we might as well be on some, mystical hocus pocus from 10,000 years ago, as far as what we today think of as absurd mythological explanations for the universe. I think we're about run out on what the current paradigm can explain without having to make some shit up. So thank you for your time. Hope you've enjoyed it. If I think of any other interesting questions or conundrum like that, I will, I guess, post them.